from folks in the audience, not new members. After that, we'll let you guys go. Maybe we'll stick around for a private session with Alex. With that, Alex, take it away.
Awesome. All right, hello everyone. My name is Alex Garcia, as Paul just told you. I'm a second-year student here at UF, and my talk is entitled Metallicity, Break Radii in IllustrisTNG Galaxies. My advisor, as you just met, is Paul Torrey, and the rest of my committee are Deshka Narayanan and Elizabeth Lada. I am going to be recording this talk, so if you're on Zoom and you don't want your video to be recorded, that's fine. You just turn off your camera. But I will be ending the recording for the Q&A session, so you don't have to worry about your voice being recorded if you don't want it to be. I'm going to start by showing you guys a picture of the cosmic web, which is the large-scale structure of the universe in a dark matter-only cosmological simulation. And so if we're thinking about a dark matter-only simulation, all we've done is we've removed the baryons from the simulation. And so naively, we might expect that this can look very similar to the cosmic web we know. So if I bring up the picture here, yeah, qualitatively, it looks very similar. We've got clusters, we've got filaments, we've got voids, everything you'd expect. But if we look in a little bit more detail, we find that in these simulations, we actually overproduce massive galaxies. And so this should raise a red flag. We've taken mass out of these galaxies in the form of baryons, but they've gotten more massive. And so the conclusion that we can draw from this is that somehow baryons are regulating galaxies' masses. But how are they doing this? To understand that question, we need to look at what baryons are doing on the smallest scales. Baryons start out in these large clouds of gas and dust, which eventually, over time, condense and form stars. Stars are important for a lot of different reasons, but primarily for this talk, they just turn hydrogen and helium into heavier elements, which we call metals. These metals are then injected back into the interstellar medium, either by stellar winds or supernova explosions, which we sort of generalize as stellar feedback. And this is a behavior that is unique to the baryons. This doesn't happen in dark matter. If we zoom out and add a little bit more context to the galaxy, we can have the complete set of interactions that galaxies undergo in their environments. We call this set of interactions the baryon cycle. And it starts by describing these exact interactions, as I've just described them, with material being distributed throughout the galaxy via feedback. It also includes material being ejected from the disk, and this can either be from stellar feedback or from AGN feedback, but no matter how it gets there, it enters the circumgalactic medium and either has enough energy to escape the system entirely, which we call an outflow, or it doesn't. And if it doesn't, it will eventually rain back down onto the galaxy as what we call recycled gas. And this gas is recycled because it's already been a part of the system and it has some non-negligible metal content with it. In stark contrast to this, though, we've got these infalling accretion streams of blue gas here from the intergalactic medium. And these streams are going to be very metal poor because there is no star formation out in the IGM, and therefore there's no metal content associated with it. And so with this, with the baryon cycle, we can see this is exactly how baryons are regulating galaxy mass. And so understanding the baryon cycle and characterizing it is a key component of studying how galaxies evolve. With this, studying the baryon cycle is studying metals. And so if we want to learn anything about the baryon cycle, we need to ask ourselves a fundamental question: what is the relationship between galaxies and their metal contents? We can answer this question in two different ways. We can either look at the stars or the material in the gas phase within galaxies. And these two things might seem very similar, but they actually tell us two very different stories about how galaxies evolve. So for example, stars tell us what the cloud was made of at the time of formation of that star. And so since stars are continuously forming and all have different ages, we can use the stellar metallicities to back out the chemical enrichment history of galaxies. The gas phase metallicity, on the other hand, tells us what the cloud is made of right now. Right now, of course, being a relative term, but it's an instantaneous metallicity. And therefore, with the gas phase metallicity, we can track where the material is at the current time. And so with this, we can use that to trace the baryon cycle. And so we're going to focus on the gas phase metallicity for our talk. And if we look at how the material in these systems is distributed throughout the galaxy, we can generate what are known as metallicity profiles, which basically just shows where the metals are as a function of galactocentric radius. Now, importantly here, we measure the gas phase metallicity in units of log OH plus 12. And we use oxygen as our proxy for the metal abundance here because it has several conspicuous emission lines in the visible. With these metallicity profiles, we find that at the center of the galaxies, there's much more metal content than on the outskirts. So this is usually fit with a line, and we can describe this line by its slope or its gradient. And so we say that galaxies have predominantly negative metallicity gradients. This is thought to be a feature of inside-out galaxy growth, wherein the stellar populations of galaxies evolve faster in the center than they do on the outskirts. And so we're building up more metals in the center faster than we are on the outside, and we're driving up this gradient. If we want to look further out in the galaxy, however, this is a very difficult challenge to do observationally. And that's because of our choice of emission diagnostics here with the oxygen abundances. These oxygen abundances, as I mentioned, are dependent on emission line diagnostics. And in order to get these emission line diagnostics, we need dense star-forming regions of gas within a disk. And as I just described, galaxies are forming inside out. So as we go further out from the center of the galaxy, these become far more rare. In simulations, however, we do not have an equivalent restriction. And so our group has done a little bit of work in this space with that, creating metallicity profiles, and we adopt the observer units here of log OH plus 12. And so this starts, as I've just described, with this nice steep metallicity gradient on the inner portions, which we can characterize with this linear fit. And this has been done in our group by a previous post-baccalaureate student named Zach Hemler. He's currently over at Princeton now. But he characterized these steep inner metallicity gradients in his 2021 paper. If we look a little bit further out in the galaxies, we find that the metallicity profile flattens out significantly. And this is corroborated all the time in observational literature in systems that we can get these resolved measurements far enough out in the disk, although they are few and far between. And so Zach is also characterizing this in his paper he's currently working on which I happen to be a co-author. But my primary work in this space is to characterize where the metallicity gradient transitions from this steep inner gradient to the flat outer profile. And specifically doing so with one radius, which we call the break radius of the system. And so I'm going to take a step back here. I've been mentioning a lot about simulations, and I need to describe the simulation model that we're using. Our group works in the IllustrisTNG simulation suite. IllustrisTNG is the successor to the original Illustris simulations, and one of the upgrades it has is that it's got multiple box sizes. So for example, this video that I'm showing you here is from TNG 300, which is the largest box, which corresponds to a box size of 300 megaparsecs cubed. But I will be presenting the results from TNG 50, which is the smallest box size. The Illustris framework, on which both TNG and Illustris are built, models several important astrophysical processes. For example, star formation, stellar evolution, galactic outflows, and many, many others. With this, these simulations don't have infinite resolution though. And so on spatial scales that we can't resolve, we have to treat the interstellar medium with an effective equation of state. And TNG uses the Springel-Hernquist equation of state, which basically just dictates that gas past a certain density threshold is going to be forming stars. And so those are that's the simulation we're going to be using. But what galaxies are we going to look at in this simulation? So as I just mentioned, we're going to be using TNG 50, but we're going to restrict ourselves to star-forming massive galaxies. Massive being defined here as 8.5 to 11 log solar masses in their stellar component. And star forming is important so that we can compare against observations. These observations, again, require these emission line diagnostics, and so they need star forming regions, and we can only really get those resolved in star forming galaxies. With this prescription, at redshift 0 in TNG 50, we get about 2,700 galaxies. We take each of these individual galaxies, find its angular momentum vector, and then orient ourselves to face down the barrel, and so we're looking at these galaxies face on. Then from there, we generate metallicity profiles by taking concentric shells of radius 100 parsecs increasing in increments of 100 parsecs, and generate the median metallicity within this shell, and then create this contiguous profile for each galaxy. But now we have 2,700 of these profiles. We want to make this a little bit more digestible, and the way we do that is we stack these galaxies by their mass, specifically doing so in bins of width 0.5 log solar masses. We also do this continuously, so the first bin is 8.5 to 9 log solar masses, the second is 8.6 to 9.1, and so on and so forth. And importantly, all the plots that I'll be showing will be quoting this from the bin centers of these bins. Then, now that we've got everything binned, we need to create what are known as stacked median profiles, which are just the sort of summary statistic of all the profiles within the current bin that we're looking. And so we do this by looking at each radius in the bin, since they're all the same separation, and we can find the median, and we generate this stacked median profile, which we are going to do our analysis on. Now that we have these profiles, we want to have a way to fit them. And we tried a couple different things with fitting these profiles. We first started just by simply having a steep inner gradient and a flat outer gradient. Then we tried a steep inner gradient, having a transition gradient, all of these again with linear fits, and a flat outer gradient. But we sort of saw the limiting behavior of this, and we decided to fit the entire profile continuously with a spline fitting method. One of the advantages of this spline fitting method is that we can compute the gradient as a function of radius, which we see on the right-hand panel here. And so now that we've fit the entire profile, we want to know where are we transitioning from a steep inner gradient to flat outer gradients. And we can see it sort of happens somewhere in this orange area. Outside of this area, we can see that we're clearly not, inside this area, we're clearly not constrained to either steep inner gradient or flat outer gradient, but we again want to constrain this to one single radius, which is going to be the break radius of the system. And in doing so, we need to recognize something here with the gradient. We notice that the gradient here is going to transition by about an order of magnitude throughout the entire disk. And so what we're going to say is we're going to offer this prescription that the break radius occurs where we change the gradient by about half an order of magnitude. But we need to be a little bit more careful than that. In Zach's 2021 paper, he characterized, again, the steep inner gradient as having a nice scaling with the 1 over the size of the galaxies that we're looking at. And so with this, this is known as the common abundance gradient, which is corroborated all the time in observational literature. And so with this, we need to be a little bit more careful with our prescription of the break radius. And so we add in this size scaling with the galaxies. So taking our prescription now for the break radius, changing by half an order of magnitude with some scaling with the size of the galaxy, and applying this to our stacked median profiles, we can see, that we've got these, I'm gonna go back one actually, so we can show this. We can see that we've got these profiles. This is just a small subset of these profiles. We've got a nice steep inner gradient followed by the transition, and we've got the flat outer gradients, and we can identify the break radius, and it seems to qualitatively agree with our expectations of where it should lie. If we look at this as a function of the stellar mass, we see that this is a monotonically increasing relationship as a function of stellar mass at redshift 0. One of the great things about simulations is we can go further back and look at relationships at higher redshifts. And so applying this exact same selection criteria and fitting method, we can do this at higher redshifts, and we obtain this relationship. We see our redshift 0 relationship with monotonically increasing as a function of stellar mass. And as we go further back in redshift, we find that this relationship just flattens out with redshift. And this is interesting because if we look at the size of the galaxies, which here we're taking the stellar half-mass radius, or the radius enclosing 50% of the stellar mass in a galaxy, as a proxy, then we can see that this exact same relationship appears. The size of the galaxies is monotonically increasing at redshift 0 as a function of stellar mass, and this relationship just flattens, as we go further back in time at higher redshifts. And so if we normalize the location of the break radius by the size of the galaxy, we find that much of the redshift and mass dependence here is either going to drop out entirely or weaken significantly. So with this, we've successfully characterized the location of the break radius. We can check that off our list. But we've done very little in describing why the profiles look the way that they do. And in order to do that, we need to take a step back here and understand what's going on physically in these systems. And so it all starts here with enrichment. And so as I described with observations with these steep Metallicity gradients, these inner profiles, we've got more enrichment happening at the center of the disk compared to the outside, again, because galaxies form inside out. And the net effect of this is that more metals are going to build up in the center of the galaxy faster, and we're going to see this gradient steepen over time. This doesn't happen on its own, though. There is more context that we need to add. And so if we take this system and we zoom out and remember what's happening on the small scales of the baryon cycle, we know that we've got material coming in from the left here, coming from the center of the galaxy. That's going to be more enriched, as I've just described. And we've got material coming in from the edge of the galaxy that's going to be less enriched. And so if we ignore adding more metals, if we pause star formation real quick, and we let this system just sort of mix over time, this is going to have the effect of homogenizing the system to one metallicity, which is sort of the effect of flattening the metallicity gradients. And so we can think of the shape of these metallicity profiles as just a competition of these two effects. The enrichment trying to build up the metallicity gradient, and mixing trying to destroy it or flatten it. We can quantify these two things with two different timescales. The first of which is going to be an enrichment timescale, which is just simply the metallicity at one location divided by the change in metallicity. And the second is going to be the gas mixing timescale, which is just going to be some radius divided by the radial velocity, or the radial exchange of material at that location. And importantly, we can create these very similar to how we create the metallicity profiles as continuous profiles as a function of radius. And since we already know the location of the break radius, we can find the value of these timescales at the location of the break radius and take a ratio and see if there's any commonalities as a function of mass and as a function of redshift. So doing exactly that and plotting it in log space, specifically the enrichment timescale over the gas mixing timescale, we find that across mass and across redshift, there are a lot of commonalities at the location of the break radius. What this is saying is that as we're traveling further out in the disk of the galaxy, the location at which gas mixing becomes significantly more dominant than the enrichment of these galaxies is the location that we see the transition occur, which qualitatively agrees with the argument that I was making before. Awesome. So now we have characterized this nice prescription as to the location of the break radius, and I've given you an explanation as to why we see the profiles look the way they do. But our predictions are only as good as our model. This could, for all we know, be a feature of TNG. And the way we want to test this is by comparing to another similar but different physical model. And so the most natural choice with this is going to be the original Illustris simulations. Although these simulations are cousins and they are similar in some respects, there are enough differences between the two to make this not only a worthwhile comparison, but an interesting one. And so I've listed out some of them here. Particularly the galactic wind implementation is slightly different between the two. TNG adds magnetohydrodynamics into the play. They have slightly different AGN feedback implementations. The threshold mass for core collapse supernovae is different between the two. And interestingly, the box size of Illustris is a bit larger than in TNG 50, which just means we're going to get more galaxies, but the resolution is approximately the same, and so this is going to be an even-handed comparison, even though they are slightly different box sizes. Obviously, there are many more differences between these two simulation models, which are well documented in the literature. Taking our prescription for the break radius, creating our stacked medium profiles, and finding the break radius in these systems in Illustris, we can create a very similar plot to the one we made in TNG 50 with the break radius as a function of stellar mass across redshift. And I'll go ahead and bring up that relationship from TNG 50 as a nice side-to-side comparison. And we can sort of see here a bit of a qualitatively different behavior. Again, in TNG 50, we see this nice monotonically increasing relationship at redshift 0, which is flattening with time. In Illustris, however, we do see an increasing relationship with stellar mass, except instead of primarily being dominated by flattening it with time, although it does appear to do so slightly, it's being dominated by decreasing in location as a function of time. And so here we're seeing, again, this sort of qualitative disagreement, but let's press on. If we look at the sizes of the galaxies again using the stellar half-mass radius of these galaxies as a proxy for their size, we can see that the relationship that the stellar half-mass radius has with the break radius is very similar. We see this relationship that sort of flattens out with time, but is primarily driven by decreasing as we go back in time. And so normalizing the location of the break radius by the size of the galaxies, we again find qualitative agreement between the two models. We find that the mass and redshift dependence of these two, of the break radius drops out significantly or entirely in some cases. And so this is good news. We can also make comparisons with these timescale profiles that I was talking about earlier. And again, between the two models, we find qualitative agreement in the sense that there is no stellar mass, there's no evolution of the location of the break radius in the ratio of these timescales as a function of stellar mass, although in Illustris there is a more clear redshift evolution. Regardless of this discrepancy, these two plots are saying the same thing. They're saying that as we're traveling out in the profile, the location where we see this transition is where the gas mixing becomes dominant, maybe not by a full order of magnitude, but by certainly some appreciable amount. It is that location where we see the transition region, where we take the break radius to be. And so in summary with all of this, we find pretty good qualitative agreement between these two models, which makes me personally happy. And so one of the things that you're probably thinking is, okay, that's awesome, we could do this in simulations, but can we do this observationally? If we were to think about a potential observational study to find the break radius, it would face several challenges. And so to recap a little bit, the typical metallicity diagnostics used in observations come from the emission of photons from these ionized regions of gas. But as I've described, galaxies are forming inside out, and so these regions of ionized gas, which are typically star formation regions, become more and more rare as we travel further out into the disk of the galaxy. Therefore, it is therefore difficult to make resolved measurements of the metallicity far enough out in the disk of the galaxy. And so the way we propose that we could get around this is combining emission diagnostics with absorption diagnostics further out in this galaxy. And the way we could use these absorption diagnostics is by using background quasar sources. Now, the geometry of this situation is pretty simple. We've got a quasar really far back in time that's got light coming towards us, and that light intervenes with the material in the outer edges of the disk of these galaxies, and we can measure the absorption from it. This is great, but these systems are unfortunately very rare. And so any study that would attempt to do this would need to do something very similar to what we're doing here, where they bin the profiles by their mass and then create a stacked profile to study the populations, more so than they can do this with individual galaxies. And so let's take a further step back and say, why is this important? And with this, let's look at the baryon cycle. We can now think of the inner portions of the disk of the gas in two portions. We can think of it as an inner enrichment-dominated portion, which we can observe with a steep metallicity gradient. And we can think of it as also having this outer mixing-dominated part, which we can observe with a flat outer gradient. And so what this does for us is it provides a potentially observable discriminator between feedback models. If we've got a situation where we have more feedback, we're going to expect gas mixing to become more dominant. And therefore, we can imagine that as gas mixings become more dominant, the profile is going to flatten out significantly sooner out in galactocentric radius, and the location of the break radius is going to move in. The opposite is true if we've got weak feedback in our models. The enrichment is going to become more dominant further out in the disk of the galaxy, and the location of the break radius is going to migrate out. And this is important because this allows us to have some prescription on what our feedback is going to look like compared to what it should be in our observable universe. Therefore, with this, we can use the break radius to understand how these baryons are impacting the mass of galaxies, which is a key fundamental understanding of how galaxies evolve. With that, thank you guys very much. These are my conclusions.